Hello students, we have started unit number 4 FM receiver, and in the last lecture we have studied block diagram of FM super heterodyne radio receiver, and we have studied frequency discrimination methods. In that we have studied slope detector and balanced slope detector. So we are going to review some of the points from the previous lecture. In FM super heterodyne radio receiver, limiter removes amplitude variations from the FM signal. After the limiter, discriminator or detector in FM receiver converts frequency variations from FM signal into equivalent amplitude variations. Slope detector and balanced slope detector uses frequency discrimination method to get amplitude variations from the input FM signal. For this purpose, tuned circuits are used. Once signal is converted into amplitude variations, then that signal is given to the envelope detector or diode detector for demodulation of information signal. In today's lecture, we are going to study phase discrimination methods of FM demodulation. We will study Foster-Seeley discriminator or detector. Then we will see ratio detector, which is the extension of Foster-Seeley detector. In the end, we will study phase lock loop method for FM demodulation. In phase discrimination method, comparison between phases of unmodulated carrier signal and FM signal gives equivalent amplitude variations. And these amplitude variations can be given to the diode detector for the demodulation of the information. Before going into the details of phase discrimination methods, we will see that how phase discrimination or phase comparison is done between the two signals. On the slide, you can see signal 1 and signal 2 of same amplitude and frequency. If we take difference between signal 1 and 2 instant by instant, then it would be 0. Means it is correspond to the 0 voltage. Now we can see the two signals, signal 1 and signal 2. They are having same amplitude and frequency, but they are out of phase by 180 degree. If we add these signals together, then the addition would be 0. Means what? It is correspond to the 0 volt. In case 2, we can see signal 1 and signal 2 having same amplitude and frequency, but they have some phase difference. If we take the difference or addition of these two signals, then it would be non-zero value, and this value will change with the value of the phase difference between the two signals. In next example, we have two signals with same amplitude but different frequency. The addition or difference of these two signals will be non-zero, and it would be proportional to the frequency of the signal 2. These examples describes us the principle behind phase discriminator or detector, which encodes phase variations between the two signals into equivalent voltage. This is a revision of FM signal waveform. On slide, we can see modulating signal or information signal, carrier signal, and frequency modulated signal. In FM signal, frequency of the carrier changes with amplitude of information signal or modulating signal. And we know that at positive peak amplitude of modulating signal, we get the compression in FM signal, and at negative peak amplitude of modulating signal we get rarefaction. So as mentioned earlier, in FM receiver at detector, which is using phase discrimination method, the phase comparison between locally generated carrier and input FM signal gives us amplitude variable signal. The instant where the phases of unmodulated carrier, which is locally generated, and FM signal matches, we get zero amplitude. As phase difference increases due to the deviation in FM signal, we get non-zero amplitude. Generally, for Fc plus del F, we get positive peak amplitude, and for Fc minus del F, we get negative peak amplitude in the envelope. This is the circuit diagram for Foster-Seeley detector or discriminator. It was invented by Dudley E. Foster and Stuart William Seeley in 1936. In circuit diagram we can see that at primary side of transformer FM signal is applied. The capacitor C1 and coil L1 forms tuned circuit. At secondary side L2 is center tapped and it forms tuned circuit along with the capacitor C2 connected parallel to it. The upper side voltage at secondary of transformer is S01 and lower side voltage at the secondary of the transformer is S02. Note polarity of these voltages. Diode D1 and capacitor C5 forms upper envelope detector. Diode D2 and capacitor C6 forms lower envelope detector. Across R2 and R3 we get V01 and V02 output voltages. Total voltage is calculated as V0 equal to V01 minus V02. Additionally, in this circuit we have capacitor C3 which is connected between input and center tap of secondary of the transformer. Also we have RFC coil. This capacitor allowed to pass carrier frequency signal from input to center tap of transformer, and this RFC coil does not allow to pass high frequencies. The voltage across the RFC is VL3. Now the phases between the carrier signal available at the center tap of transformer and FM signal are compared and proportional output voltage is generated. We know that the frequency of FM signal is continuously changing. It is changing from Fc to Fc plus del F, then from Fc plus del F to Fc, from Fc to Fc minus del F, and from Fc minus del F to Fc. It will go on changing continuously, where Fc is the carrier frequency and del F is the deviation. Now, the instant when FM signal frequency is equal to the frequency of the signal available at the center tap of secondary of the transformer is equal, then it induces S01 and S02 equal and opposite. For the frequency of the FM signal Fc plus del F, S01 will be greater than S02, which gives us the output voltage positive. When frequency of FM signal is Fc minus del F, it makes S02 greater than S01, which gives us V0 less positive. We can say it is a negative. So this can be very well explained with the help of phasor diagram. This is the phasor diagram at resonance. Means The frequency in FM signal matches with the carrier signal available at center tap of secondary of the transformer. As mentioned earlier, at this situation when the frequency of carrier and FF signal matches, it generates equal and opposite secondary voltages. In phasor diagram, VL3 is the voltage across RFC, that is of carrier signal frequency obtained from input. S01 and S02 are induced secondary voltages and they are equal and opposite of each other. The phase difference between VL3 and SO1 is 90 degree. V01 and V02 are resultant voltages across R2 and R3 respectively. Phasor diagram for the frequency greater than the resonant frequency means what? When the frequency of FM signal is Fc plus del F. Now in the phasor diagram we can see that for this situation S01 is greater than S02, which results into V01 greater than V02, which makes output voltage more positive. This is the phasor diagram for the situation below resonance. Means when the FM signal frequency is less than carrier frequency. So we can see in the phasor diagram that S01 is less than S02, which will result into V02 greater than V01, which makes V02 less positive, or sometimes it may be negative.